Right, okay, so carrying on from this comparison of Kirchoffs laws in series and parallel, just like when we did working out total resistance, you did it in series, and then you did it in parallel, and then we'd have to consider combined circuits as well, where you've got a series bit and a parallel bit. We'll have to do the same thing with Kirchoffs laws. And it's not confusing, but it just gets weird because one minute you're talking about voltages and then the next minute you're talking about currents. Because whenever you're employing Kirchoffs laws about series stuff, then you're talking about voltages. But as soon as you're using Kirchoffs laws in a parallel circuit, then you're actually talking about currents. So that's where it gets a wee bit confusing. Just a quick run through of some of these questions here. You know, what are the answers? So state Kirchoffs' first law. So his first law is all the currents in a parallel circuit add up to the supply, or all currents at a node sum to zero, or all the currents coming out of a node must equal the current going into the node, something like that. As soon as you're talking about nodes, that means that I know you're talking about parallel circuits, because it's parallel circuits, they have nodes. And then state Kirchoffs' second law. It's supposed to say ensure you state which type of circuit it relates to. So Kirchoffs' second law is his voltage law in series circuits. So all the voltages in a series circuit add up to the supply voltage, or all the voltages in a loop sum to zero, you know, something like that. Right, okie dokie. What type of circuit is that? So that's a series circuit, there's no nodes in it, it's a series circuit. What's the current through R2? So this was asking you to recall the fact that in a series circuit, if there's only one path, it's the same current no matter where you measure it. So if the current here is 2 amps, then the current through R2 is 2 amps. The current through R1 is 2 amps. The current from the supply is 2 amps. If Vs is 9 volts and V1 is 3, we know that V1 plus V2, so 3 plus something equals 9, V2 must be 6. 3 plus 6 equals 9. That's the maths of that stuff. It's the same all the way down here. Calculate the missing voltage supply. 6 plus 8 plus 2, 16 volts is your supply in question 10. Which voltage drop will be bigger, V1 or V2? So this is where you're looking at the resistances, and in the video I had said larger resistances get larger voltage drops. So that's 16 ohms. So V2 will be bigger than V1 because 16 ohms is bigger than 10 ohms. So V2 is the biggest. Put the voltage drops in order of size. So really that's just look at the resistances, put them in order of size, and then match them up. So smallest first, so that will be the 1 on the 9 ohms, so it's V3, V1, V2. In this one, what will the two voltage drops be? Because the two resistance values are the same, that means V1 and V2 will be the same. So V1 will be half of the supply, V2 will be the other half. So V1 and V2 are 8 volts each. And then it's the same kind of mathematical practice in this one. That's a parallel circuit because there's the nodes. These two resistors are in parallel with each other. What's the voltage across R2? So that's just the opposite. You know, all I've done is ask the questions in the same order, but it's like the opposite question. So in a series circuit, the currents are always the same. We're asking you to remember that. In a parallel circuit, come on. In a parallel circuit, the voltages across these two are the same. And in this case, the voltage across this parallel branch from node to node is 9 volts. So the voltage across R2 is 9 volts. The voltage across R1 is 9 volts. If IT is 9 amps, right, so it's 9 amps going into the node, and I1 is 3 amps, what's I2? It must be 6 amps. 9 in would be 9 out, so 3 plus something equals 9. I kept the numbers the same as the previous question as well. Just to impress upon you how similar they are, but you're just changing what you're talking about, changing the context of what you're talking about. So that's the same as all these. Calculate the missing current from supply. So that's 8, 3 and 2. That's 13 amps being drawn from supply. Which current will be bigger? Again, this is about looking at the resistance values. So the current will be bigger through the smaller resistance. Remember, resistance is about resisting the flow of current. Larger resistances result in smaller currents. This asks which one will be bigger. So that's the smaller resistance. So you get 10 ohms there. That will be the biggest one. I1 is the largest. Put these in order of size. Smallest first. So that's the biggest resistor. So it's I3, then I1, then I2. And then what will the two currents be? So again, the two resistance values are the same. So the two currents will be the same. And they will each be half of 4 amps. So I1 and I2 are 2 amps each. So that's the kind of process that we're looking for. So now let's consider a combined circuit. Right, so let's say you've got a resistor in series with a parallel branch. And let's talk about Kirchoffs law on this. Alright. So let's talk about voltages first. So you'll have a supply voltage, whatever that is, and that'll appear from here to here. Yeah. So you know that Kirchoffs law says that voltages in series are up to supply, so there's Vs. So this resistor is in series with this parallel branch. So there's a voltage drop here, which we would call V1. And then there's a voltage drop. I haven't drawn this very well, have I? There's a voltage, I'll go the other way. And then there's a voltage drop across the parallel branch, as if it was, because remember, which we call V2. So V1 plus V2 equals Vs. Remember, we could redraw that. You know, we could work out that total resistance and redraw it as an equivalent resistance like that. So that would make that circuit just two resistors in series. Yeah. Then you'd have V1 and V2. And what's important to note is that if at any point you've got V2, that means you've got the voltage across that resistor and the voltage across that resistor, because those voltages are the same because that's a parallel branch. So it's V2 across the whole parallel thing. So that means it's V2 across one of the resistors, and it's also V2 across the other one, because in a parallel branch they get the same voltage. Alright, so that's voltages. And then, so you treat the parallel bit like an equivalent resistor in that regard, okay? When we talk about currents, obviously the first thing that happens in this circuit is like a series thing. So if that's IT, then it's going to be IT through that resistor. But then IT will get to that node, and then you get that split. So you'd have I1 and I2, and then it's just the same. That's Kirchoffs' first law. Then it becomes IT again over here. So what I'll do is I'll set up some questions that are the same as the last two worksheets, but the circuits will all be combined series and parallel, and then the idea is, can you identify the missing value using only Kirchoffs' law? We're only going to use Kirchoffs' law, or that idea about if these things, I'm not going to ask you to do any resistance calculations yet, okay? I just want to focus on Kirchoffs' laws. But I might ask you a question where the two resistance values are the same, so that, and that might mean that you should know, maybe not instinctively, but you should be able to calculate really easily what the value will be, like halving it or doubling it or whatever, you know, something simple like that. So, but they'll start off easy, and then I'll throw a couple of hard ones in later on. Right, so let me get a wee set of questions up. Give me a second. Right, okay, so first set of questions, I'll do another set after this. So here you've got two resistors in parallel in series with R3. What I would suggest you do is draw this circuit out for each question and put the values in, because it will make more sense. You know, it helps you visually as well as textually, okay? So the first one is if the voltages, so this is testing your kind of series Kirchoffs' law down to question 4, and question 5 is testing your kind of Kirchoffs' first law, the currents ones, okay? Then I start to get a little bit cryptic at the end there. The last two questions, well, question 8 is a bit of a trick question, so you know, watch out for that. And question 9, draw it out, and it says here if R1 and R2 are equal values, okay? So you know, just pick two values at the same and put it next to it, and it might help your thinking, might help your logical reasoning. Take your time and try to get it right, okay? Let me make up another set on a different question. Right, so again, just read the questions carefully. The first three are kind of relatively straightforward. So the first two are just about voltages, the third one's about currents in the parallel branch. The fourth one is about that kind of, you know, resistance values equaling each other, so what should that do to voltages. The fifth one, read the question carefully. Again, you should be drawing these circuits out and annotating them for every question, so that you can check your logic about what Kirchoffs. Always look back at the Kirchoffs' original law that you're trying to utilise in the question. And in question 6, yeah, it's not necessarily a trick question, but you know, just read it carefully. The other thing is, I've messed about the number formats every now and again. You'll notice this 27 milliamps, okay? That means times 10 to the minus 3. Okay, so that's like a really small amount of amps. And then 0.027 amps, I've expressed that amps value there. So if I had like 12 milliamps, I'd have to write that in amps before I do any calculations. I should always be using amps. So what I do is write down a 12. I know that milli is 10 to the minus 3. So the decimal point would have been there. But because it's 10 to the minus 3, I move it 3 places to the left. 1, 2, 3. So that's my actual number there. 0.0012. So 12 milliamps becomes that when I put it on a calculator. Alright? Bear in mind, always watch your unit for multipliers. It's like kilograms, 1,000 grams. Milliamps, 1,000th of an amp. Right, okie dokie. So, all the best with that.